Here you can see the primary coil with taps built into it. Moving along, it is inductively connected to a long, fine Tesla coil-like secondary. And inductively connected to that, we have a 3-layer coil at the end, which is our pickup coil, or second primary coil. Here's the entire device on display. Again, our primary coil here, secondary coil, second primary coil or pickup coil. This goes straight into the switching diode right over here. Rectifies the current of the second primary coil. And that is fed into these two output prongs right here, which we can use to power any load we want. Here again is the apparatus as shown in the circuit diagram earlier. The black cord and the white cord here are our outputs, which will be unaffected by the resonance of the primary circuit and are being driven by the coils in the collecting circuit. And here we have a small switching diode to rectify the current so that it can run DC motors. It's currently on, it is in resonance. Now I will show it running a small tiny geared motor here. It's hard to see, but it's actually going pretty fast now. You can hear it. Thing's trying its heart out. Now the interesting thing about this setup is that I can switch loads on it automatically without throwing it out of resonance, despite the fact that they are of different inductive capacity. This motor is also running perfectly fine, and I can even do one about 3 times larger than that. Yeah, that one is spinning away. Here I have a voltmeter hooked directly up to the output, so no current is flowing through, or very little, since it's a 1 megohm meter here. But as you can see, there's about 83.6 volts on the output, and this is a 75 volt switching diode, so that makes about sense. If it goes over that, it's going to go backwards through the diode, and the voltage won't climb any higher than that. Here we have the device running in resonance, and it's powering an inductive load. Right now we're measuring the voltage across the terminals of the larger motor, and as you can see by the meter, we're running at about 13.19 volts DC. Here again you can see the same inductive load, only this time we've made a break in the circuit to allow the multimeter in to take current measurements. As you can see, according to the multimeter in the upper right hand corner, we're running at about 35.06 to 04 milliamps. Here again I have the multimeter inserted in the inductive load circuit so as to take current measurements, but this time I'd like to show you twisting the knob to fall out of resonance and how drastically that changes the amount of power and current flowing through there. Even a slight twist to the dial and the motor goes severely down. Going back up, past it, and you can see it, resonance, and going the other direction, immediately falls off. Here again we have the device with the current meter inserted in to take amperage readings. It's still running the same inductive load, and I can understand if a person were to argue that maybe the motors were of the similar inductive value and so the device is still able to run in resonance. However, I'd like to show how narrow a bandwidth we're running at here and how finicky this device actually is. While touching the primary, either primary does nothing. Touching the secondary here creates a vast diminishing effect in the power output. As you can see, the current dropped to 14 milliamps and the motor has stopped spinning. Letting go, it skyrockets off again, the motor takes off, and we're back up to the same amperage. Here again I have the device running, but rather than an inductive load, I've attached two 82 microfarad capacitors for a total of 164 UF. These are rated to 450 volts, however you can see that they're still only reaching about 69 volts due to the limiting capacity of our switching diode there. As you can see, short-circuiting it causes a bit of a spark, and it fills immediately back up. Here I have another inductive load running in the background. You can hear the noise coming from it. Some people might be wondering, what about the power input here? That's an incredibly important question. Unfortunately for me, I don't have any tools that can accurately read AC current in this high of a frequency, but I can use the old light bulb trick that I used last time to show you the increased impedance upon hitting the resonant frequency. Here's the same little trick I demonstrated in the first video. I'm using a light bulb here in series with the primary to indicate its impedance. As the impedance goes up, it'll look like a large resistor, meaning little or no current is being drawn from the signal generator, which is again acting as our circuit controller and source. As we hit the resonant frequency, note as the light bulb goes dim and the motor skyrockets off. You can see it going through several values here, getting bright and stuff like that again as it hits different resonant points. And there's resonant frequency. Little current is being drawn from the source.